Hello GATE aspirants. Welcome to part 4 of GATE Atomic and Molecular Physics series. Question number 25. The number of spectral lines allowed in the spectrum for the 3-2D to 3-2P transition in sodium is. Now for 2D, we have L is equal to 2 and S is equal to half. That means value of J will be L plus S to L minus S. So this will be 3 by 2 and 5 by 2. And for 2p state, L is equal to 1, S is equal to half. So J will be half and 3 by 2. Now selection rule is delta J can be 0 or plus minus 1 and delta J or J is equal to 0 to J is equal to 0. This transition is not allowed. So firstly we have 5 by 2 and that transition to 3 by 2. So here delta J is equal to plus 1, so this is allowed. Then 5 by 2 to 1 by 2. Here delta J is equal to 2, so it is not allowed. Next start with 3 by 2. So 3 by 2 to 3 by 2. Here delta J is equal to 0, so it is allowed. And 3 by 2 to 1 by 2. Here delta J is equal to 1, so it is also allowed. So the number of spectral lines will be 3. Next question. In a normal Zeeman effect experiment, spectral splitting of the line at the wavelength, here lambda is given 643.8 nanometer, corresponding to the transition 5,1D2 to 5,1P1 of cadmium atoms is to be observed. The spectrometer has a resolution of 0.01 nanometer. The minimum magnetic field needed to observe this is. Here resolution is given, that is delta lambda 0.01 nanometer. Now separation between Zeeman components. Delta nu is equal to EB by 4 pi m. Now delta nu, it can be written as C upon lambda square delta nu, because nu is equal to C by lambda. So delta nu is equal to C, and 1 by lambda square is minus 1 by lambda square into delta lambda. So from here we can write it. Minus sign we won't consider because we need only magnitude. So from here B is equal to, B will be equal to this 4 pi mc into delta lambda upon E lambda square. So this is equal to 4 into 3.142 into m, mass of electron, that is 4.1 into 10 to the power minus 31, into C is 3 into 10 to the power 8, into delta lambda is 0.01 nanometer, so 10 to the power minus 9, upon E is 1.6 into 10 to the power minus 19, into lambda is 643.8 square into 10 to the power minus 18, and this comes out to be 0.5173 Tesla. So that is value of B. So 517, so this is nearly equal to 0.52 Tesla. So option B is correct. Question number 37. The spacing between vibrational energy levels in CO molecule is found to be 8.44 into 10 to the power minus 2 electron volt. Given the reduced mass of CO is 1.14 into 10 to the power minus 26 kg. Planck's constant is given. The force constant of the bond in CO molecule is. Now here reduced mass is given and spacing between them is given. So we know K is equal to mu into omega square, and omega can be written as delta E upon h cut the whole square. So this will be equal to 1.14 into 10 to the power minus 26 into delta E is 8.44 into 10 to the power minus 2, and that is in electron volts, so we have to convert it to joule. So into 1.6 into 10 to the power minus 19 upon 6.2626 into 10 to the power minus 34 upon 2 pi as well. So into 2 pi the whole square. And if you calculate this, then value of force constant K comes out to be 186.98 Newton per meter. So here option C is correct. See, we know F is equal to Kx, and F can be written as m into acceleration, and this will be K into x. So from here acceleration is K by m into x, which is omega square x. So from here you can write K is equal to m omega square, but here we will use reduced mass. Next, statement for linked answer. In a Smith model of nuclear magnetic moments, mu is E h cross upon twice mc gl l bar plus gs s bar, where the symbols have their usual meanings. For the case J is equal to L plus half, where J is the total angular momentum, the expectation value of S dot J in the nuclear ground state is given by. Now we have to calculate S dot J. So we should write it in terms of S and J. So J is equal to L plus S. So we can write L is equal to J minus S. So taking magnitude, so this will be J square, J plus S into J minus S. So this will be J square plus S square minus 2S dot J. So from here S dot J, it will be equal to J square L square. So we have to consider that, which is minus sign. So this will be J square plus S square minus L square upon 2. And if we are taking expectation value on both sides, so it will be on both sides. So this will be equal to J into J plus 1. Value of J square is J into J plus 1 plus into H cut square is also there, into S plus 1 minus L plus 1 upon 2, and this whole thing into H cut square. Now here it is given that J is L plus half. So J is L plus half and S is half. So we'll substitute it here. So this will be J is L plus half. So we have H cut square by 2 into L plus half, then L plus half plus 1. So that is L plus 3 by 2 plus S is half. So half into 3 by 2. So that is 3 by 4 minus this will be L into L plus 1. Now we have to simplify it further. So this Sj is equal to H cut square by 2 common. L into L is L square plus L by 2 plus 3 by 2 L plus 3 by 4 plus 3 by 4 minus L square minus L. That is H cut square by 2, L square minus L square. L by 2 plus 3L by 2, 2L minus L, so that is L. And this is 3 by 4 plus 3 by 4, that is 3 by 2. So plus 3 by 2. But we have J is equal to L plus half. So here L plus half will be J. So this will be H cut square by 2 into J plus 1. So here option B is correct. J plus 1 by half. Next question. For the O17 nucleus, A is equal to 17, Z is equal to 8. The effective magnetic moment is given by this expression where G is also given. Then we have to calculate. Now A is equal to 17, Z is equal to 8. That means they are all paired up, and neutron number will be then 9. So these are unpaired. So we can write 1s 1 by 2. It will contain 2. Then we have 1p 3 by 2 4. Then 1p 3 by 2, then 1 by 2, then 2. So these are 8. Next one 1d 5 by 2, so 1. So last will be in this 1d 5 by 2. So that means J is equal to 5 by 2, L is equal to D, so 2, and S is equal to half. And here this J is 5 by 2, so that is 2 plus half. So this J is equal to L plus S. So this is L plus half. Now for that, this is for neutron. So for neutron, we know this moment, effective moment is equal to minus 1.91 into mu n. And this is also given here. So we can write G J mu n, and that is equal to minus 1.91 mu n, and this is for neutron. So mu n will cancel out, and from here we can write G is equal to minus 1.91 upon J. But J is 5 by 2, so this is minus 1.91 upon 5 by 2, and that is equal to minus 0.764, which is nearly equal to minus 0.77. So here option B is correct. So these were all the questions from GATE 2013 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.